Okay, so let's continue where we stopped last time. We were in the middle of proving that actually our root system that comes from semi-simple algebra is an abstract root system. So let us recall what is an abstract root system. First of all, you have Euclidean space. With inner product, right? Then R, a finite subset of E, is called abstract root system. If, first of all, R spans E, then this, so for every alpha and beta from R, this number n alpha beta, which is 2 alpha beta over beta beta, is integer. And 3 is that reflection of one root with respect to another is also a root. So if alpha and beta are roots, then S alpha beta, which is beta minus twice the projection of beta on alpha, is also a root. And if additionally we have 4, which says that alpha and so if alpha and C alpha are roots, then C is plus minus 1. Right. So if additionally we have 4, then R is called reduced. So R is reduced. So this is a reminder what we deal with. And our proposition was the following. We considered the real span of roots. So now let R, so I guess now let me take R to be the root system of a semi-simple algebra. Okay, let me organize this better. So I'm writing the same thing. I just don't want to squeeze it into a small line at the top. So what's our proposition is the following. So let G be semi-simple. H is a Cartan subalgebra of G. Then you have root decomposition. Then, and also let me introduce H star R. It's a span, linear, real span of R. So these are two different R's. This one is bold and this one is not bold. These are real numbers, these are roots. So this, of course, lives inside H star, right? So we introduced all the stuff, and also final thing that we would like to consider is form on H star, which is given by the killing form on H. Okay, so form on H star induced by killing form. Okay, so then, first of all, H star R together with this form restricted to H star R. Right, so this pair gives me an Euclidean space, is an Euclidean space. And the second that R is a reduced abstract root system on H star R, is a reduced abstract root system on H star R. Okay, so we proved number one last time. But on the way of proving one, we also proved check this condition for R. So n alpha beta is an integer, and that we also proved also last time. Right, this was a weight in some representation of SL2. Right, so that's why it was integer. All right. So maybe even we can recall what. So we had this V alpha beta, right, which is sum of the following: gk plus so g beta plus k alpha, and k running over integers. so we prove that this is irreducible representation of SL2, but we need particular SL2 which is corresponds to the root alpha. Okay. So here alpha and beta, they're of course roots. And moreover, we proved that G beta plus K alpha is yes. So you should help me out here, because so it's some it is some weight subspace of V alpha beta, right? Of which weight? So it's either n alpha beta or n beta alpha. So that's we need. So I think it was beta alpha plus 2k. So that's so n beta alpha is of right. So if k equals 0, then n beta alpha is the is exactly the weight in V alpha beta. All right. And so that's why we had this. So we also had, like, we denoted this as mu last time as well. Okay. So that was what we had. Right. Again, let me maybe denote this as mu. Right. So let me fix alpha and beta and denote this as mu. So I'm going to prove that if my alpha and beta are roots, then the reflection is also a root. Okay. So right. So let me take G beta. So suppose alpha and beta are roots. So take two roots, alpha and beta. Then G beta is not 0, right? Because beta is root. On the other hand, because of this line, it is exactly V alpha beta of mu. Therefore, so now let's again recall representation theory of SL2. So it is kind of symmetric with, so weights are kind of symmetric with respect to 0. Not kind of, but they're symmetric, right? So therefore, if I have weight mu, then I have weight negative mu, right? So then, so since this one is weight, then negative mu is weight, and V alpha beta of negative mu is not 0. So the point is that I would like to see now that this is this corresponds to GS alpha beta. Then I proved everything. Okay. So my I would like to see that V alpha beta of negative mu is exactly GS alpha beta. Maybe I will leave the formula for now here. Okay, so let me see. I would like to use this thing again. All right. So what is V alpha beta negative mu in terms of, so what k should I take here? Right? So this is mu. So k should be negative mu, right? Right? For this thing to be negative mu inside parentheses, I should take k to be negative mu. So therefore, I have, using again this formula, V alpha beta of negative mu is G beta minus mu alpha. Right? But what is B minus mu alpha? It's B minus, and mu is this number n beta alpha, and n beta alpha is this thing, 2 alpha beta over alpha alpha alpha. So this is my mu, which is also n beta alpha, right? But you can compare now. This is exactly S alpha beta, just by definition of this reflection. Therefore, we have that V alpha beta negative mu is exactly GS alpha beta, right? But we know that this is not 0. Therefore, GS alpha beta is not 0. Then by definition of roots, this is also a root. So roots are exactly elements of H star such that we have corresponding eigenvalue, common eigenvalue for H, right? So corresponding G with such corresponding to such element of H star is not 0. So it's just by definition. So therefore, this is root. Okay, we proved 3. We proved 2. So 1 follows automatically, right? Because of course R span H star R just by construction. And what we need to check now is that it is a reduced root system. So we proved that it is an abstract root system. Now we need to prove that it is reduced root system. Okay. Right. So what are our options? We know that. So suppose I have alpha and beta again are roots, and beta is C alpha, where C is some complex number. Right. So then we would like to consider n alpha beta. Again, this is 2. I have to write alpha beta, but I can write alpha C alpha, right? Over alpha alpha. So it is 2C actually. And this should be integer. Also, I can take n beta alpha, and this will be 2 over C, actually. And this is also should be integer. This restricts the values, the possible values for C to the following. Maybe you tell me what. So from these two conditions, what are the possible values for C? Two, okay, yes. 2, 1, right. Can be 3. Okay, so from this to from this one it is half an integer, right? Right, but we cannot go more greater than 1, right? Because of this condition. Greater than 2 because of this condition. 1, 2, but also yes, 1, 2 plus minus 1/2. Yes, plus minus 1/2, and this is it. So C is only from these two conditions. When we know that C can be only this. Now we would like to rule out this 2, this 4, right? We can just it's enough. I claim that it is enough to see that C cannot be 2. It is enough to see that C cannot be 2. Because suppose C is negative 2, then I can take my root, I can take, instead of alpha, I can take negative alpha. Then I'm back to the situation where C is 2. If my C is 1/2, I can just rename alpha and beta, like switch them. And then I'm back to the situation where C is 2, right? So I can just, take, play with the roots to go back to this situation, right? So we would like to see that C is not 2. You can see it like this. Again, this is our main instrument. Look at this irreducible representation. But in this irreducible representation actually contains an adjoint representation of SL2. So I claim that V alpha beta it includes SL2 alpha itself. SL2 alpha itself. I think I don't even need this. I need just V alpha. Sorry, no beta. So V beta. So let's recall. V alpha is CH alpha plus direct sum of GK alphas, right? Where K runs over Z minus 0, right? So therefore, this is, but SL2 alpha, it has triangular decomposition, right? It is exactly CH alpha plus G alpha plus G negative alpha. Right? So this is a subspace of this guy. But also this is subrepresentation. So what is the action of SL2 in all this V alphas with alpha betas? So this is just adjoint action, right? Or restriction of adjoint action of G on itself, right? So SL2 acts on here, inside this representation we have subspace which is adjoint subrepresentation. And the adjoint representation is reducible. But this guy is also reducible. Right? So both V alpha and SL2 alpha are irreducible representation of SL2 alpha it means that V alpha equals SL2 alpha. In particular, all other terms that we have here, they are just zeros. In particular, G2 alpha is 0. In particular, G2 alpha is 0. So twice a root cannot be a root. Okay, so 2 alpha is not R for any alpha from R. That's exactly what we would like, what we wanted. Okay, so we proved the proposition. So now we have another instrument, to work with semi-simple algebras, which are abstract root systems. So these are root systems. So these are some vectors in Euclidean space, and you can draw them. Say something about length of vectors, angle between vectors, and all this stuff from just usual geometry, Euclidean geometry, and draw pictures. And today on the seminar we'll draw pictures, right? So okay, and some of these pictures will be very familiar from the first semester, actually. All right, so now we would like to study. Now our goal actually is to classify all root systems in actually reduced root systems, right? So from now on, let us talk only about reduced root systems, okay? So goal to classify all reduced root systems. So from now on, assume that all abstract root systems we are talking about are reduced. Also, what it means, classify, you need a notion of isomorphism of root systems, right? Of course, if you just rotate it or maybe rescale it, we don't care, right? So let us introduce the notion of an automorphism of root systems.
I have a question.
Yes.
For a semi-simple algebra, we have root system correspond to that, right?
Yes.
And is the inverse correct?
Yes, yes.
Inverse is correct. Oh, we have the root system.
Right. So actually, the classification of semi-simple algebras are related to classification of reduced root systems.
Related means?
Related it's bijective. So for for every root system, you can construct a semi-simple algebra and the other way around. Yeah, yeah. It's not obvious. It's a big theorem, but you need like a list of relations. So that, of course, some relations we already know, right? Which is, how elements of H alpha commute with elements from G alpha and so on. But you have more relations, maybe not, but you do have. And these are called Serre relations. We'll introduce them. But for now, let us try to classify all just abstract root systems. So, okay. Definition. So let R1 and R2 in my Euclidean space be two root systems, two abstract root systems. Then a linear map phi from E to E is called an isomorphism of R1 and R2 if, so let me continue here. Well, we have these numbers which are very important, n alpha beta, all right? And you have these numbers for R1 and for R2, okay? So let me call it like this, write it like this, n phi of alpha, phi of beta is n alpha beta. So this one corresponds to the second root system. This one corresponds to the first one. And also, of course, I would like to, so if, maybe before that I should write if phi of R1 is exactly R2. First of all, it maps roots of R1 to roots of R2, and it actually leaves these numbers invariant, in particular angles, right? Invariant. Okay, so now let us so this is the notion of isomorphism. So let us introduce the group of automorphisms of R, which are just, the group of all isomorphisms from R to R. In particular, you have some subgroup there, which is generated by reflections with respect to roots. Okay. So definition subgroup of automorphisms of R generated by S alphas, right? For each alpha in R is called the Weyl group. Of R. So this is also a very important object, the Weyl group. All right. You see so obviously the Weyl group is a finite group, right? Because automorphisms are finite. R is finite finite set, so therefore all automorphisms cannot be a finite group, right? So we'll denote it as W. So we denote the Weyl group by W capital. So note W is a finite subgroup of, let me write like this. So all orthogonal transformations of E, right? Because reflections, they leave angles and distances the same, right? And finite because it's a group, just it is group permuting elements of finite subsets. So that's why it's finite. All right. What can be said about Weyl group? We'll use it from time to time. For every root alpha and an element of a Weyl group, we have the following. If I would like to apply W to alpha and consider reflection like this, then it's given by conjugation of S alpha with W. So for every alpha and W, we have this. Proof. Okay, another very important thing for studying criticisms are these hyperplanes with respect to which we reflect. Hyperplanes which are orthogonal to roots. Okay, so let us denote such hyperplanes as L alpha. So let L alpha be the hyperplane orthogonal to alpha. Okay. Then if I take L, hyperplane orthogonal to W of alpha, it is the same as if I take hyperplane orthogonal to alpha and apply a transformation W to it. This is just because each element of the Weyl group doesn't change angles, right? If I have something which was orthogonal to alpha, right, that goes to something to orthogonal to W alpha, right? So that's why this is true. On one hand, we have this. So let me take V from here. Okay, so take V from this LW alpha. So consider this. Then, because of this, V is in the image of some V prime with respect to W, where V prime lives in L alpha. Okay. So then let me take the right-hand side here and apply it to V. Okay. So I would like, so my goal is to see that this thing leaves this hyperplane invariant. Okay, this is my next computation. Okay, let's check it. So let me take V and apply right-hand side there to V. So I have W as alpha W inverse. So this is V is W V prime, right? So therefore this is W as alpha and then V prime, because W inverse and W this W and this W inverse, they just cancel each other. V prime is from L alpha, right? And reflection with respect to alpha doesn't change the plane which is orthogonal to alpha, right? So therefore, this is W V prime, right? Which is V. So I checked that this guy does not move any vector which is in L alpha. Okay. Right. The next check is that I take this element and apply it to alpha itself. Sorry, not to alpha, but to W alpha. I would like to see that the result is the negative of what I started with. So it takes W alpha and just, gives me opposite. Okay, so the check is the following. So I take this, apply it to W alpha. Again, this cancels. Then S alpha applied to alpha is negative alpha, right? So reflection with respect to the hyperplane orthogonal to alpha, right? So this will W of S alpha of alpha, and this is W of negative alpha. So minus of what I started with, right? So I apply it to this and get negative this. So I claim that these two checks actually prove that my element W S alpha W inverse is exactly a reflection with respect to the root W of alpha. So it leaves the plane LW alpha not touched, and the root W alpha goes to negative W alpha. It means that it is a reflection with respect to this plane. You just can take, so if you're not convinced, you just can take basis in the hyperplane, right? So let me draw pictures. you take some basis in hyperplane, and you have this root alpha, right? So you take any point in your Euclidean space. In my case, it's just R3, okay? So it will be decomposed somehow. It will be linear combination of this 3 in this case, right? So what happens? This, if now I apply this element, what happens? This will not change, and alpha goes to the negative alpha. Well, in this case, it should be W alpha, right? This is this hyperplane, right? So it means exactly that now that my point, right, the only component that will, in its decomposition on this basis, will change is exactly this one, which is orthogonal to this plane, and it changes to the opposite. So it's exactly reflection. Okay, now, did I convince you now? Okay, so this is check, and we proved the lemma. Very well. So the next notion that we'll introduce for root systems is regular element. So an element T from my Euclidean space is called regular if I compute inner product with any root system, with any element of root system, and it's not 0. So for any alpha in R. Why do we need these elements? Mostly for introduce polarization in and work with polarizations in R. So what is a polarization of a root system? Polarization is you just need to choose which roots are positive and which are negative. So you divide your E in two halves. Okay, this can be formalized using a regular element like this. So definition a polarization of R is a decomposition of R into two disjoint subsets, R plus and R minus, such so where R plus are all roots such that alpha with T is greater than 0, and R minus are all roots such that alpha with T is less than 0, but this is for some regular element so I choose an element, right? And which is regular, means that I choose a plane actually that does not contain any of roots. And then on one side of this plane, I say all roots are positive, on the other side are negative. So that's basically what I'm doing. Of course, a lot of regular elements give me the same polarization, right? If I just, change it a little bit, once it doesn't intersect any hyperplane L alpha, it's just the same polarization, right? If I intersect, then it's something different. Some root becomes which was positive now becomes negative, but that's not what we want. Okay. Okay. So right. So I said positive and negative, but formally I didn't write definition. So elements of R plus are called positive roots. And of R minus, respectively, negative roots. Okay, this is just terminology. Okay, and so once I chose polarization, I would like to consider inside R plus some roots which are called simple. Okay, so now the definition is coming. Sure.
Do you mean that the composition didn't depend on choice of T?
It depends on choice of T. Not too much. So you have a finite number of classes of T that will give you the same polarization. Yeah. But still depends. Yes. Right. Definition. Root, positive root, is called simple if it is not a sum of two positive roots. Okay, so this is very important because actually when we will classify root systems, we classify not root systems themselves, but sets of simple roots. So actually our goal now is to study how, if we can recover simple roots, roots from simple roots. And if I have different choices of simple roots, how they are related. Okay. But before that, we have the following proposition, which is also very important. That pi, so remember R spans E. So what, okay. I never introduced what is pi. So pi, let pi be, so let pi denote the set of simple roots. So once I chose polarization, pi is chosen already, right? So choosing of polarization, choosing of the set of simple roots, kind of the same. So proposition that pi is a basis of E. So R spans E, so now we made our set of roots smaller, and we now would like to prove that it's like perfectly smaller, right? So it still spans E, but now it's also linearly independent. So proof proof is the following. So first, let us prove that pi is not too small, so it still spans E. So let's prove that pi spans E. What to do here is clear. You just take some root and try to decompose it as a linear combination of elements from pi. Right? If you can do this, like finite linear combination, then still R itself spans E, and each root you actually can decompose as a linear combination of pi, then pi spans E. Right? So let us take, and of course I can start decomposing positive root, right? Because of course just positive root spans span E, right? Of course, if you take positive root, the negative of this root is negative, right? Okay, so first we will need the following observation. So let T be the regular element, or one of the a regular element, right, that defines polarization for us. So let T from E be regular such that alpha of T is greater than 0 for all alpha from R plus. Right, so then observation is the following. So if alpha and alpha 1 and alpha 2 are all positive roots, and we have alpha is alpha 1 plus alpha 2, then the inner product of alpha 1 with T is strictly less than inner product of alpha in T. And the same for alpha 2, of course. Right? Well, just because you consider, you apply inner product with T of both sides, right? And the sum of these two is exactly alpha T, so therefore this follows. Very well. We will need this to make the following process finite. So take beta. So if it's simple already, then we are done, right? It's already a linear combination of itself, right? So our goal is to write beta as a linear combination of roots from pi. So we would like it to be positive, but not simple. So then we can write beta as sum of two positive roots. So if both beta 1 and beta 2 are simple, then we are done, right? So if one of beta 1 or beta 2 is not simple, then we continue. We write beta 1, then as a sum of two positive roots, and beta 2 is a sum of two positive roots. If beta 1 or beta 2 are not simple, decompose again. And so on. So you just continue this process. So because of this observation, this process is finite, right? You have finite number of roots, and then on each step, you decrease this number, alpha and t, right? When you decompose, you decrease, you decompose, you decrease. And you have finite number of roots, therefore, at some point, you have to end up with two simple roots. Okay, so let me call this observation star. So by star, this process is finite. So therefore we are done. So therefore beta is actually sum over alpha i's with some coefficients ni, where alpha i's are from pi, and also actually we have that these coefficients are positive integers. We didn't need that for the fact that pi is Pensky, but still it's a good observation. Right. So therefore we proved that pi spans E. So now let's prove that pi is linearly independent. For that, you will need some knowledge from what we'll discuss today on the seminar, but you already did this. Okay, so so I would like to use the following observation. So y1. So maybe just some claim that if I have two roots and they are simple, and alpha is not beta, so they are distinct, then this thing is less or equal than 0. Okay, so this, how to prove that? So proof is the following. Proof of claim, I mean, right? Proof of claim. Okay, so let me take actually hyperplane which contains both alpha and beta. Actually not a hyperplane, but actually plane, right? Two-dimensional plane that is spanned by alpha and beta. So let L alpha beta be the span of alpha and beta. And I also don't want beta to be negative alpha because, well, it's clear that it's true if beta equals negative alpha, right? So I really would like L alpha beta to be two-dimensional plane, okay? Okay, assume alpha not equal to negative beta. Then, if I take this plane and look which roots actually belong to this plane, right? I would like to consider intersection of R and L alpha beta. And then I claim that this intersection is a root system in L alpha beta, right? So then R alpha beta, which is intersection of R and L alpha beta, is a root system in L alpha beta. And so this are root system of rank 2. People say what it means rank. I never introduced it. So let me so this is root system of rank 2. So by definition, rank of E of R is just dimension of E. Nothing hard here. Okay. It's just dimension of the plane or like space in which you live. Right, but root systems of rank 2. So first of all, why is that true? That okay, I take my plane, intersect, like look what at all roots that are in this plane, and the corresponding set is a root system itself, like maybe smaller and of smaller rank, but still root system. You just can check that all parts in the definition we have they actually true, right? And alpha beta they doesn't care about restrictions to the subspaces, right? So once you have a root already there, then projection will be along this plane. It doesn't really matter, right? So then alpha beta will be integers. Again, they are just the same as in the big root system. But then reflection, right, with respect to root, is actually a reflection with respect to so you have a plane. Right, so again, let's draw pictures, right? So you have alpha, beta, right, and this plane, right? Reflections in a big space, right? I need to take a hyperplane which is orthogonal to roots which belong to this plane, right? Right. So therefore, it will be reflection in some hyperplane which is orthogonal to L alpha beta, right? But reflection orthogonal with respect to L alpha beta just sends vectors in L alpha beta back to vectors in L alpha beta, right? So reflections in a big subspace correspond to reflections in this subspace as well. If I take reflections with respect to roots which are already in L alpha beta. So this system is also closed with respect to reflections as well. Okay, it's harder to say than to understand. Right. So you just can, think about it for a minute and see that it is true. But now we have quite a limited number of reduced root systems of rank 2. We will all discuss them together. And you can check just, there are 4 of them, right? So you can check for them that it is true. So let's check today on the seminar when we will draw them. Okay? Okay, so.
Excuse me, Professor.
Yes.
I wanted to ask, when you talk about the simple roots, are you counting in the simple roots the reflection also or not?
No, so simple roots are positive roots by definition. So if I reflect, so if I reflect a positive, no, that's, so okay, so what do I mean by am I counting reflection? So some reflections some reflections might take simple roots to simple roots. That's okay.
Okay.
Yeah.
So basically when we talk about simple roots, the reflection may or may not be a part of it.
So reflection is some transformation, and root is element of a vector space. So these are objects of different kinds,
Yes,
right?
So my
Yeah.
conclusion was the way you are defining simple roots is that they cannot be written as a sum of the other roots.
Yes.
Right?
Yes.
But the reflection is a different thing and it's not like same as the saying, oh, it's a sum of the others.
No. So for reflection, you cannot say that it is sum of some other transformation. So for transformation, it's a group, right? You don't have sum there, right? So actually, there is some relation to that, right? For example, if you have root which is a sum of other 2 roots, then there is some relation in the Weyl group in reflection corresponding to the sum of roots and reflection corresponding to the terms. But it's not a sum. It's not a linear, of course, because you don't have plus sign in your group. Yeah. Okay, so let's proceed. So this thing, I claim that, okay, if I take 2 roots, then I always can check statements about only two roots, just checking these 4 root systems that we will discuss today on the seminar. Okay? So then I check alpha, beta less or equal than 0 for rank 2 reduced systems. Okay, so I would like to use this now to prove that pi is linearly independent. So by contradiction, so suppose, so let alpha 1, alpha, I don't know, R, be distinct simple roots which are linearly independent. That maybe not let, I would like to suppose, right, for the sake of contradiction. Are distinct simple roots which are linearly dependent. Then there exist some numbers positive numbers Ci such that I have the following: sum over Ci alpha I equals sum over Cj alpha j. So I runs on the left-hand side over some subset I of these indices, and j runs over some subset j of these indices. So this I and j, they are subset inside the set of numbers from 1 to r. So what I did, so suppose they're linearly dependent, right? So therefore I can write down like a sum like this, like sum ai alpha I equals to 0, where at least one ai is not 0, right? So this is what linear dependence means. So I from 1 to r. But then I just look at which AI is positive and which is negative. And so if AI is positive, I will just call it Ci. If it's negative, I move corresponding term to the right, and call negative AI to be Ci. And then I get something like this. Right, so all the negative terms, I just move to the other side. That's it. Right. So let me. So AI, if AI greater than 0, then Ci equals AI. If AI is less than 0, then Ci is negative AI. So that's how it is related. So both sides here are not yes. So right. So suppose first that both sides are not 0. Right. Of course, it can happen that all AIs are positive, for example. Right. Then I just have 0 here, and all CIs are just all AIs. Right. So if so let us denote V to be some left-hand side and right-hand side of this equality, right? Ci is I runs over I alpha I, and which is the same as Cj alpha j as j runs over subset j. And what's important here actually is that I does not intersect j, right? So indices of positive coefficients and indices of negative coefficients, they distinct. All right. Then let me consider V, just the norm of V. Okay. Right, so if I have a norm of V, so the first equality I plug into the first, place here, so I from I. And use the second equality to plug into the second place here. So Cj alpha j, j runs over j. So this is this is just sum over I from I, sum over j from j, Cij of alpha I, alpha j. But I and j cannot are not right. So I and j, they are not the same. I cannot equal to j, right, in this sum, because we have this. So therefore, these are distinct simple roots. Because of our observation, all this is less or equal than 0. All this alpha i's with alpha j. So we proved, we discussed that if I have two simple roots distinct, then the scalar product will be less or equal than 0. That was our claim. So therefore, Ci, Cj here, right? So this is positive, and therefore the whole thing is negative, which is contradiction. Okay, so here I actually assumed that so all this is true if under assumption first that V is not 0, right? So it's not true that all AIs are positive or all AIs are negative. Okay. So if V is not 0, then it's like that. So I have to say something. So if V is 0, right, then I have something like sum over Ci alpha I equals to 0, right? Where these Ci's are greater or equal than 0, and I is from 1 to R. Right? It just happens, suppose it happens that all Ci's are positive. Say, if they're all negative, right, the argument is similar. So suppose they're all positive. But then let me take T that defines polarization for me, right? So let again T be regular such that alpha with T is greater than 0 for all alpha from R plus. And let me compute the inner product of the left-hand side with T. Right? So what I have on the left, I will have so sum over Ci alpha I with T. I would like to look at this. But then alpha I with alpha i's, they are simple, therefore they are positive. Therefore, the inner product of alpha I and T is greater than 0. Right? So therefore, this is sum over Ci I from 1 to R, alpha I and T. This is greater than 0. This is greater or equal than 0. Then, and moreover, at least for some index, Ci is strictly greater than 0. Right? That's our assumption for linear dependence. So therefore, the whole thing is strictly greater than 0, which is contradiction. Again, right? This should be 0 on one hand. On the other hand, I prove that it's greater than 0. So this is contradiction. So for both cases, v is not 0, v equals to 0. We get a contradiction. Therefore, our assumption that we have some set of distinct simple roots which are linearly dependent is not true, right? So therefore, by contradiction, pi is linearly independent. Okay, so we proved that pi is a basis. Okay, tell me how much time do I have? What? No? 3 minutes. Okay, that might be a good place to stop.